Hello everyone, in this video I will explain on how FIR or finite impulse response filters work in digital signal processing, and I'll walk you through this Python code step by step. FIR filters are commonly used because they are stable and can be designed to have linear pace, which is very important in many signal processing applications. First, I define the basic parameters. I set the sampling frequency to 1000 Hz and create a time vector that spans 1 second. This time vector represents our discrete time signal in the time domain. Next, I generate two sinusoidal signals, a low-frequency sinusoid at 50 Hz and a high-frequency sinusoid at 200 Hz, with a half the amplitude. These two signals represent useful low-frequency information and unwanted high-frequency components. I then combine these sinusoids and add random noise to simulate a real-world noisy signal. The first plot shows this noisy signal in the time domain, where we can see that the waveforms look irregular because it contains multiple frequency and noise. Next, I design the FIR filter. I set the cutoff frequency to 100 Hz, which means frequency below 100 Hz should pass through the filter, while frequencies above 100 Hz should attenuated. I also specified the number of taps as 51, which determines the filter length and directly affect how sharp the filtration transition will be. Using the filtering function with a Hamming window, I design a low-pass FIR filter, and obtain the filter coefficients. I then compute and plot the frequency response of the filter using the freeze function. From this plot, we can clearly see that the filter allow low frequencies to pass by significantly reducing the magnitude of higher frequencies beyond the cutoff. After designing the filter, I apply it to the noisy signal using the filter function. I then plot both the original noisy signal and the filter signal in the time domain. Comparing these two plots, we can observe that the filter signal is smoother, indicating that the high frequency components and noise have been reduced, while low frequency sinusoid remains. Finally, I analyze signals in the frequency domain using the fast Fourier transform. I complete the FFT of both the noisy signal and the filter signal and plot them magnitude spectra. In the noisy signal spectrum, we can clearly see strong frequency components around 50 Hz and 200 Hz, along with the broadband noise. In the contrast, the filter signal spectrum shows that the 50 Hz component is preserved, while the 200 Hz components and high frequency noise are greatly attenuated. Interpreting the output, this clearly demonstrates how FIR filter low-pass filter effectively removes unwanted high-frequency components while preserving the desired low-frequency signal, which highlights the practical importance of FIR filters in digital signal processing applications.